We'll start the live session. Welcome everybody to the weekly live tutorial sessions on mechanics and control of robotic manipulators. So this course is actually hosted by IIT Palakkad. It's been hosted by the faculty Dr. Shant Kumar. I hope you have been covering the lectures regarding week 1. And I am actually the TA for this course, MCRM. And the purpose of this weekly tutorial sessions would be to have a brief summary of all the topics that has been covered during the weekend, and also to solve some sample problems, which would most probably would help you to solve the weekly assignments. So I suppose the deadline for the week 1 assignments are still not over yet. We may still have some time for the deadline of week 1 for week 1 quiz. So if you go through the sample problems that we would be covering during this session, it would be easier for you to crack the tutorials. So despite saying that, as you might have already seen through the lectures, the topics covered in this in the first week are basically an elementary recap to linear algebra systems. We only cover elementary transformations such as pure rotations or pure translations, and then when we go to the next week, from week 2 onwards, we would be dealing with the kinematic modeling of robotic manipulators. What we would be covering for week 1 would be just a prerequisite for the kinematic modeling of robotic manipulators. So yeah, we'll get on with the session. So moving on, the topics covered for this week are a brief introduction to robot mechanics, specifically mechanics of robotic manipulators. We would also give a brief introduction to the kinematic problems of robotic manipulators, which are classified as forward and inverse kinematics. We would also discuss on how to describe the position and orientation of a rigid body, because in this course, we would be assuming that the robotic manipulators is basically constituted of several rigid bodies connected one after the other. And description of a rigid body require, how you would navigate among frames. So we would cover that topic. And further, we would also discuss the topic on transformation metrics, which is actually a very compact way to represent composite rotations as well as translations together. And then we will cover the topics with compound rotations. That would be the end of week 1 syllabus. So the way I have designed this lecture is, as you can recall, these sessions, these weekly tutorial sessions, will go on for 2 hours. So I thought of splitting the first half of the session to dedicate it for a brief recall of what all the topics that we have covered during the week, and the later half, the second half, we would dedicate to solving problems. So just quickly going through some of the key definitions that we have seen through the lectures of week 1. So we'll start with the definition of robot itself. So as per the Robot Association of America, the industrial robot is actually a reprogrammable, multifunctional manipulator designed to move materials, parts, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. So the robot is actually derived from a Greek word, robota, which basically means a slave. So the word was first coined in fiction, basically, not in scientific circles. It came out as part of a play, which was later adopted in in scientific circles actually. So and this, even now there is still there is no conclusive way of defining or a conclusive way of defining what a robot is. Some people would classify uh, a machine that is capable of performing an automated tasks as robots. Some people would argue that you have to have incorporate some sort of an intelligence in order for a machine to classify as a robot. So plenty of circles define robot based on their own ideas or principles. So one another definition of robot, which only came quite recently, is something an intelligent agent. Robot is an intelligent agent, physical or virtual, capable of doing a task autonomously or with guidance. So a robot, in the modern definition, does not really have to be physical. What you would imagine when you first hear about robot, you would the first thing that come to your mind would be a physical entity basically, but that does not have to be, because as you know, today is the world of chatbots. What you see, these chatbots are you might have experienced all these chatbots replacing customer services these days. So it does not have to be virtual. It does not have to be physical. It can also be a virtual entity. So but keeping aside all these definitions aside, what we are dealing with in this course, the definition of the robot that holds for this course is as follows. A robot is an electromechanical machine or mechatronic system with with sensors, electronics, and guided by computers and controllers. So whatever we have defined, it does not apply to what we are dealing with the course. The virtual aspects or the virtual entities you don't consider for this course. We are only specifically focusing on electromechanical machine or mechatronic systems, incorporated with sensors, electronics, and which are guided by computers or controllers. So, and where and when we would use robots. So, where and when should we deploy robots? This the answer to this lies here actually, is what we basically call as 4Ds of robots. So the Ds, as you can see, these are the key areas where we would deploy the robots. Where the tasks, if the human were to do these tasks, which are considered to be dull, dirty, dangerous, or difficult, we could replace a human being. It would seem more ideal or appropriate to replace human being with a robot to perform tasks which are dull, dirty, dangerous, or difficult. And these basically change with respect to what era or what phase that we are living on. Earlier, when the robots were first being employed, it was only dull, dirty, and dangerous tasks where we would use robots. And now we would also use it for tasks which are inherently difficult for human beings to perform. So as we acquire, technological as well as computing advances, we can still, employ a robot in much more complex applications where, a human being can be, replaced. So yeah, that is about where we would employ robots. We would employ robots or deploy robots for tasks which are dull, dirty, dangerous, or difficult. And I'm sure you can easily find tasks which can be classified under each of these categories. And speaking of robotic manipulators, one important thing that you would often come across is a term called effector, actually. So the key definition of effector is any robot or a robotic device that has an effect on the environment, right? And there are various classes of effectors. So the first one depicted here is an effector called a manipulator. right? And the second is actually a mobile robot. That is also another kind of effector. And the third one over here, what you see is a mobile manipulator. So it's basically a combination of the attributes of a manipulator as well as a mobile robot. So what effect does a manipulator have on its environment? So the purpose of a manipulator is to manipulate the objects around it, right? For example, if there are objects in the robot's workspace, again, that is also another term that we would discuss later on. So if the manipulator's purpose is actually to manipulate the objects around it, maybe to pick this object and to place it somewhere else, that can be classified as manipulation, or simply keep it and do some operations such as drilling it, right? So the effect of the manipulator on the environment is to manipulate the objects around it. So those sort of effectors we would call it as manipulators. And what about the second class? What about mobile robots? So the mobile robot basically operates or locomotes by driving its own wheels, right? And depending on the direction of the rotation of the wheels, it can either move forward, it can move backward, or it can rotate about its own vertical axis. It can move sideways like this laterally. It can also move diagonally. All sort of motions are possible. But what is the effect of a mobile robot on its environment? So in case of a mobile robot, the effect would be the locomotion of the effector itself, right? In case of a manipulator, it has a fixed base. The base is always fixed, and the links are free to move relative to each other. Whereas in the case of a mobile robot, the effect on its environment, which are nothing but the reaction forces applied by these wheels on the ground, the effect would be the motion of the uh, device itself or motion of the mobile robot itself. And the mobile robot will have attributes, combined attributes of manipulators as well as a mobile robot. So that is what an effector is. And another definition that we would come in the second half of this course is something what we call a controller. So we look at a more detailed definition of controller when we get there. But just to give a brief glimpse of what we are dealing with, the controllers, uh, to get effectors produce the desired effect on the environment based on the robot's tasks. So the controller's aim or the controller's task is to get the effectors produce the desired effect on the environment. For example, these effectors are actually modulated or actuated using motors. And in order for us to accurately or repetitively guide these motors, we would need some control. We would need some feedback control to make sure that all the motors would actually follow what they are being commanded to. Because there would be a lot of things that we cannot account for, maybe disturbances in the environment, or maybe some manufacturing clearances, manufacturing defects. All these things make the robot move in an unpredictable fashion, and the controller essentially ensures that it strictly tries to follow what it has been commanded to. That's what controllers are about. We will discuss more about controllers on the second half of this course. Okay, so since the course is more about robotic manipulators, we would uh, discard these two sort of effectors. Right? This is a topic for a different course, actually. So manipulators, again, further can be classified into three more categories. These are basically a general category. There are even more categories. But in the context of rigid manipulators, these are the three major categories that one should be aware of. So the first is called a serial manipulator. The first category over here is called serial manipulator, because in serial manipulators, the manipulator is actually an assembly of uh, links or rigid links connected one to the another, actually connected serially, like a tail to end configuration, right? So this rigid link would be connected to the fixed base through a joint, maybe a revolute joint, and the second link is connected to the first through another joint, and so forth, one over the another. Whereas over here, what you see is a parallel manipulator. Right? So here, a platform over here, as you see, a platform is connected to the fixed base through multiple legs, parallel legs. And each of these legs will have their own actuators. An actuator, maybe a telescopic arm, which can, extend or contract its length. So this specific manipulator has 6 such legs, and each of these legs are telescopic. So depending on how much you actuate these individual legs, the platform's position as well as orientation can be altered. You can have 3 translational degree of freedom or 3 rotational degree of freedom, depending on how much you actuate each of these 6 actuators. And the key difference between the serial manipulators are, in case of a parallel manipulator, as you can see, since it is supported by 6 legs, they are, they can be used for heavy payload applications. And due to the fact that they also have 6 legs, they are much more accurate. Because in case of a serial arm, the huge portion of the weights of a manipulator's arm is contributed by the motors themselves, right? And because of this weight, the robot itself will have to carry a lot of weight because of the motors. And because of that, there could be some deflection or bending, because the weight of the motors itself is actually quite high. Whereas in the case of a parallel robot, the motors or the heavy actuators are more or less near to the grounds, more or less much more closer to the grounds, and they have relatively low velocity. And because of that, the moving inertia is actually less in case of a parallel manipulator. So that inherently makes the manipulator much more accurate, as well as much more capable for uh, much more capable for heavy or heavy duty, high payload manipulations. And one another thing is that in the workspace, or the maximum volume of space that serial arm can reach is inherently higher for a serial manipulator. For example, if you consider a person, uh, forgive my crude representation of a person. So if you consider each of its hands as a serial manipulator, each of the person's hand can describe or can reach a certain volume of the workspace. I'll try to give a better description of that. Yeah, I'm ignoring the other aspects. I'm only focusing on the hands, the fingers, right? So if you consider each of these hands as a serial manipulator, each of these hands, maybe I'll draw one figure actually. So the red part corresponds to this arm, the right arm, and the blue hand corresponds to the left arm. So each of these arms can have a very large workspace. So you can consider each of these arms as a serial manipulator, right? You can see it for yourself, like how the maximum range. If you extend your arm like this, fully extended, it can reach maximum position, which is a fully extended configuration. And if you fully retract, that will be the minimum configuration that your hand can reach. But what happens if you try to reach a point when you grasp both of your hands? That will be much limited compared to one of your hands being fully stretched. right? So the reason is that if you try to plot the workspace when both of your hands are, combined, for example, this being one hand and this being another hand, the overall workspace would be very less. The reason is that because in case of a parallel structure, yes, sorry about that. Let me share my screen. Okay, so the reason is that when you have a parallel like structure, for example, if you clasp both of your hands together, the total workspace will be the intersection of the two individual workspace. For example, if the blue circle is actually the is the workspace of the left hand alone, and if the red circle is the uh, yeah, if the red circle is the workspace of the right hand alone, and the total workspace of the parallel structure of the left plus the right combined would be the intersection, actually, would be the intersection of the left as well as the right circles, actually. So the workspace of a parallel robot would be much lower. Workspace of a parallel robot would be much lower compared to a serial robot, inherently, actually. Okay, so then the third class would be a combination of serial as well as a parallel manipulator. We call this as a hybrid manipulator. So this is nothing but a combination of a serial plus parallel architecture. Okay. So yeah, so some more key definitions actually that we would be using throughout the lectures or throughout the courses. So now that we have seen what is the difference between a manipulator and a locomotion device, the manipulator is a system of set of bodies arranged or connected as chain with the help of joints. So similar to what we have seen over there, it's a set of bodies connected as chains, and each of these bodies are connected using joints. And the commonly used joints for a robotic manipulator are, revolute joints, which will only have a 1 degree of rotational freedom. And the second be prismatic joint, which also is a single degree of freedom joint, but will only allow translation along one axis. So pure rotation or pure translation. And the second definition is configuration, actually. So the configuration is a complete specification of location of every point in a manipulator. So suppose we have a manipulator comprising of two links. So this is link 1, this is link 2. And over here we have the fixed base. So the link 1 is connected to the fixed base using a revolute joint, like so. And link 2 is connected to link 1 using another revolute joint. I'll label this as R1 and R2. And as per the definition, the configuration is the complete specification of the location of every point of the manipulator. So the configuration means we should be able to locate, or we should be able to identify each and every point of each and every point of the manipulator. So basically we can do so by two coordinates. So since the manipulator has two links, we can identify the configuration using two parameters. The one being theta1, it's nothing but the angle link 1 makes with the horizontal, and theta 2 could be the angle link 2 makes it with link 1. You can choose any two parameters however you want. You can choose theta 1 to be again an angle where theta 2 makes with the horizontal. That is also fine. But for this course, we would stick with the convention where the first joint always makes an angle with respect to the horizontal ground, and the second joint makes an angle, or the configuration of the second joint is specified by an angle with respect to the first uh, or the previous link, such as theta 2, and all the subsequent links, similarly to how we have described theta 2. So, for example, if we had one more link over here, like for example theta 3 or link 3 like this, so the configuration of link 3 would be described by an angle theta 3 with respect to link 2, and so forth, so on and so forth. So that is configuration done. And another definition is workspace. Actually, we have already talked about what we mean by workspace. That is nothing but the total volume swept out by the end effector of the manipulator executes all the possible motions. So one example, one of the most frequently modeled and studied manipulator is something called a 2R manipulator or an RR manipulator, which is short of a manipulator having two revolute joints, R and R. That is how we got the name RR manipulator. So the total volume swept by the end effector would be, if you consider this both of these arms fully stretched, it will actually describe a circle, right, centered at this origin. And if you consider both of these arms to be contracted on its own, again it would describe another circle centered at the origin. So the volume would be, or the workspace would be, the area between these two circles actually. So the volume is actually a context actually. So not all robot can describe a volume. For example, this robot, it can only work on a plane. So, workspace can be defined in terms of areas as well, right? For example, this is a planar robot which only lives in a plane. So it's the total volume that, or the total area, or the total number of points that the tip of the robot, or this end effector, as we call it, can achieve. It's a collection of all the points the tip of the robot, or this end effector, basically can realize. And there are two such workspace over here, the two classifications being a reachable workspace and the second being a dexterous workspace. So the reachable workspace is nothing but all the points of the workspace where the robot can reach in any orientation, right? Whereas dexterous workspace, it has to be a point where the robot can reach at any arbitrary orientation. Not only you have to reach at that point, you also have to realize or achieve that point with any arbitrary orientation. Like for example, if you consider your own hand, if you try to fully extend your arm, try to imagine a point where you can reach by fully extending your arm. And you can only reach that specific point by a single orientation. You cannot reach that point or achieve that point with any orientation because your hand is fully stretched. But any point in between, for example, if you consider the tip of this pen, you can actually achieve or realize this point with any orientation, right? If you consider this tip of this pen, I can reach it by this orientation, any arbitrary orientation I can reach, right? So set of all points where I can reach with any arbitrary orientation, such points are called dexterous workspace, and reachable workspace are excluded. If you exclude the total workspace from the if you exclude the dexterous workspace from the total workspace, what you have left is the reachable workspace. which are essentially the points that you can reach only with minimal orientations. Okay, so I hope that is clear. And another key terms that we would be revisiting a lot during these sessions are the first one being the degree of freedom, and the second one is degree of manipulability. And I suppose you would know this. Degree of freedom is nothing but the minimum number of independent variables required to describe a system. Or in essence, description of a system essentially means describing the configuration of robot. And degree of manipulability basically is the number of controllable inputs or active joints. For example, if you consider an arm with only a single link connected to the ground with a single joint, a single revolute joint. So this arm has a finite length. Maybe you can call this as L. So how would you describe, how many variables do you need to describe the position of this arm? You only need a single variable, theta, right? Describe the configuration of the robot at any point of any of its instances, right? For example, if the arm is rotated like this, if you rotate it like this, you can you can fully describe each and every point of this robot using one parameter alone, theta. Right? A single parameter alone can describe all the points that is lying on this link. So that essentially means the degree of freedom of the robot. Whereas in case of a two-linker robot, a two-link manipulator like this is the first joint connected to the ground, R1. This is the second joint connecting link 2 and link 1. You actually need two variables or two independent variables to fully describe the configuration of this specific manipulator. So that is basically the degree of freedom. And the degree of manipulability is the number of controllable inputs or active joints. So in the context of a serial manipulator, the degree of freedom and degree of manipulability are essentially going to be the same. So the number of controllable inputs for 2R robot is 2, because you would be having a motor here and you would be having a motor here. And in case of a single link manipulator, the degree of manipulability would be 1, because you only need a single motor, or you only need to control a single input to fully define the configuration of the input. Right? Yeah. Whereas in the case, there are cases where these may not even be true, because there are robots with 7 joints actually. So the degree of manipulability would be 7, but the degree of freedom would still be 6, because in space, as you know, you only require 3 translations and 3 rotations to fully define rigid body. But some of them may even have 7 or 8 motors to have some sort of redundancy, because, for example, if the intended path for a robot to move from one point to another is blocked by an obstacle, the redundancy would enable the robot to go through another path to the set goal position. So in some cases, having the redundancy is desirable, especially when the robot is working on a dynamic environment, and you will never know when an obstacle may come, within its workspace, and somehow it'll probably will have to navigate around the obstacle to reach its goal position, and the redundancy would enable the robot to, achieve that. So, but in most of the cases, especially from the context of our course, the degree of freedom and degree of mobility for the serial manipulators that we would be considering would be more or less the same. So that's that. Then the next topic that we would be covering is the kinematics of the robot manipulator. So if you have taken any mechanics courses, you might have come across the terms, kinematics, kinetics, statics, and all those things. So the the key term is actually dynamics. And under dynamics, you will have two such classes. The one is called kinematics, and the second being kinetics. So dynamics essentially means the study of change of state of a system with respect to time. The state can be change of motion or change of position or change of the force profiles. It can be anything. But kinematics, strictly limits itself uh, on the study of motion without considering what is actually causing these motions. So, for example, here, as per the definition, kinematics is the study of motion, without considering the forces or effects that causes the motion. Right? For example, consider if a body is rest and suddenly it is accelerating and it reaches some other velocity. Right? So kinematics only deals with velocity, position velocities, and accelerations. And as you know, this acceleration occurs because of some unbalanced forces. So we are not dealing with forces in kinematics. We don't consider what causes these accelerations. We are treating the motion exclusively as fully isolated from the forces, which or forces or efforts which causes this motion. And later, when we consider dynamics, we would also, consider the forces aspect. How the forces causes the change of motion of a robotic manipulator, or the change of forces at the motors would make the robot to move to realize a different configuration. Yeah. The next definition is kinematics describe the relation between the motion of the joints of the manipulator and the resulting motion of the rigid bodies which form the robot. So as we said earlier, it's simply but the study of the linkages which makes or which whose assembly essentially makes a robot manipulator. And there are two problems in kinematics that we would be interested in to solve. The first being forward kinematics problem, and the second being inverse kinematics problem. So the forward kinematics essentially says the forward kinematics determines the configuration of the end effector for a given relative configuration of each pair of adjacent links. So for example, if you have a 2R manipulator, so we would be using this 2R manipulator to explain a lot of concepts. So this is link 1, this is link 2. The first link is connected to the base using a revolute joint. The second link is connected to the first joint using a revolute joint. Right? Yeah. So as we have already discussed, we require two parameters or two coordinates to fully define the uh, configuration of this manipulator. And you can also consider a gripper or a tool at the end of this manipulator. So depending on the inputs or the inputs that you give to these joints where you have where you have motors, what would be the final position achieved by the tool or the end effector? So if you consider the length of the link as L1 and length of the second link as L2, you can basically map the configuration space. So the configuration space, what we define here, or the task space variables, like we basically map this task space variables theta1 and theta2 to the operational space variables x and y, right? So this theta1 and theta2, we would consider these as inputs to be given to the motors. We would call this vector of these variables as configuration variables, or another name to call them is joint space variables. Right? And we would like to map the configuration space variables or the input that we are giving onto the motors to another set of coordinates, what we call as task space variables. We would call this as task space. Another name is operational space. Operational space variables. Right. So the forward kinematic problem is to find out the task space for a given set of joint space variables. Right. For example, if I give an input theta1 to the first link and an input theta2 to the second link, where would the final end effector, what would be the position that the end effector reach? One example is if theta1 is 0 degree and theta2 is 90 degree, the robot manipulator would something like this, like an L-shaped configuration, right? Or if theta1 and theta2 are 45 degrees each, so theta1 is 45 degree, theta2 is 45 degree. So the robot manipulator would something like this. The first one is 45 degrees, and the second one is again 45 degrees. It looks something like this, right? So that is what forward kinematics is. And you would from week 2 lectures, you would be introduced to the tools or methods to describe the forward kinematics of serial manipulators. And the second problem we would be dealing with is called inverse kinematics. So in inverse kinematics, in inverse kinematics, basically, for a given set of task space variables, for example, if we want the robot to go to a specific location in a plane, for example, X and Y, what would be the command that we should be giving to the motors? So given X and Y, what is theta1 and theta2? So that would be the inverse problem actually. So this from theta1, theta2 to X and Y, this is forward kinematics. And from the task space to the joint space, this would be inverse kinematics. So the methods and techniques to solve both of these problems, forward kinematics and inverse kinematics, we would be covering from week 2 onwards. So next we move on with the description of position and orientation of a point, for example, in instance. So consider a point P in space, right? So this is described by a vector with respect to a fixed frame of reference, what we call as frame A. And the frame A is actually defined by this basis vectors X, Y, and Z. So you can basically define or describe this point P using vectors along these unit vectors or these basis vectors along X, along Y, and along Z. Right. So to reach P, you would need to traverse Px distance along X, Py distance along Y, and then Ez distance along Z. Right. So basically, more or less straightforward to describe a position of a point. The second aspect or the second thing that we would be discussing is the description of position and orientation between two frames. Right. Earlier, we considered the point because in case of a point, we only need to consider its position. How the point is oriented is immaterial because in case of a point, orientation does not make any sense. It does not make any difference. But when we are comparing two frames, for example, consider two frames which are originally coincident, coincidental, and the second frame B is actually at an angle or is rotated compared with ZA. So how would you describe the relative orientation of frame B with respect to frame A? So we do this by expanding this matrix. For example, so if you consider XA, YA, and ZA to be unit vectors along A axis, vector along A axis, and XB, YB, and ZB are the unit vectors along the rotated B axis. How would we describe the orientation of frame B with respect to frame A? So it can be done by expanding this matrix of dot products. So XB dot XA, XB dot YA, XB dot ZA, YB dot XA, YB dot YA, YB dot ZA, ZB dot XA, ZB dot YA, ZB dot ZA. So like if you expand all these dot products, you will be able to obtain the rotational matrices between the two frame of references. And why is this important? How is this important to our course? Because in case of rigid manipulators, a rigid manipulators is comprised of rigid bodies. And the way that we would mathematically model rigid bodies is by replacing or is by substituting a frame of references in place of these rigid links. Because you can pretty much, if you know the position and orientation of the frame of reference, you can actually know you can basically determine all the points of the rigid body because the frame is rigidly attached to that rigid body. So the mapping between the rigid bodies is essentially can be easily represented by mapping between frames of references that are attached to the rigid bodies. So in case of robotic manipulators, there is relative rotation between frames as well as relative rotation between frames. So that is why, essentially mapping essentially describing the orientation between frames is of importance. So we'll look this in more depth. What does this mean actually? So this column, we can look this as individual columns. So the first column basically depicts the angle between the XB frame with respect to XA, YA, and ZA. And the second column basically depicts the angle between YB with respect to XA, YA, and ZA. And same for the third column, which basically denotes the angle between ZB with respect to XA, YA, and ZA. So, like for example, if you consider both the frame B and frame A to be coincident, having no relative orientation initially, and now we are rotating frame XB with respect to XA by an angle theta. Right? We are rotating XB. We are rotating frame B along XA by an angle theta. So there is an angle between XB and YB and YA as theta. This would be 90 minus theta, and this would be theta, and this would be 90 minus theta. Sorry. This angle would be 90 minus theta. So based on this representation, how would you define a rotation matrix if the rotation is a pure rotation about x-axis? So as per the first column, the rotation between XB and XA axis So since the rotation is about x-axis, there is no angle or there is no orientation between xb and xa axis. So the dot product between xb and xa axis, xb dot xa cos 0, this is essentially 1, right? So that basically makes 1 as the first column. And since the angle between xb and ya is 90 degrees, and xb and za is also 90 degrees, the remaining two entries are 0. And for the second column is basically the angle YB makes with respect to XA, YA, and ZA. So YB makes an angle theta 1 with respect to YA. So the projection of YB on YA would be, sorry, YB on XA. First, we have to consider XA. So the orientation between YB and XA would be 90 degrees because XA is out of plane. So that is 0. Cos 90 is 0. YB and the direction cosine or direction between YB and YA would be cos theta, and YB and ZA would be sin theta, right? This would be cos theta. This would be sin theta. That is what these two entries are about. And if you resolve ZB along XA, YA, and ZA, ZB along XA is again 0 because XA is out of plane and ZB is within the plane. And the dot product between ZB and XA would be 0. ZB and YA. So yeah, if this angle is theta, this would be sine theta, right? And since this projection would be along negative YA, it will be minus sine theta. And if you resolve ZB along ZA, this angle being theta, projection would be cos theta. That is the third entry here. So that is how you compose rotation metrics. So another example is a pure rotation about YA axis. So I've defined earlier the out of plane axis was XA. Now the out of plane axis is YA. And the other two axes are defined with respect to the right hand screw rule. So if the pure rotation is now about YA, what is the angle between XB and XA, YA, and ZA? So if this is theta, this will be 90 minus theta. This will be theta. And this angle will be 90 minus theta. So the angle between XB and XA would be cos theta. Projection would be cos theta. XB and YA would be, it's 0 because it's out of plane, that is 0. And XB and ZA would be, the projection would be this much. And since this is the negative direction, it will be minus sine theta. Projection of YB on XA would be 0 because both of them are perpendicular. Projection of YB on YA is 1 because they are parallel. Projection of YB on ZA is again 0 because they are perpendicular. This angle is perpendicular. And similarly, projection of ZB on ZA is sine theta actually. ZB on XA. ZB on XA would be, this would be sine theta. ZB on YA would be 0 because ZB and YB are orthogonal. They are 90 degrees apart. And the projection of ZB on ZA is this much. That would be cos theta. So a pure rotation about y-axis is defined by this matrix. A pure rotation about x-axis is defined by this matrix. And similarly, the pure rotation about z-axis is defined by this matrix. Right? So this is z-axis, this is x-axis, and this is y-axis. So like once we have fully described the elementary rotations about x, y, and z, we can use a combination of rotations about x, y, or z to realize any arbitrary orientation. Like we can compound these three rotations, elementary rotations, so that any arbitrary rotations can be represented. So yeah, now we would deal with the description of position and orientation, both of them combined. which basically involves a mapping between translated frames. The first part is mapping between translational frames. So like, for example, we have a fixed frame of reference, frame A. We'll assume this to be fixed to the ground. And the second frame would be floating. It could be on a floating rigid body. And our objective is to define the position of point Q with respect to frame A. That is the ground. So if you consider this vector addition, the point Q, position of point Q with respect to frame A is simply the position of frame B with respect to A plus frame position of point Q with respect to frame B, which is nothing but which is actually given by this vector addition. But you also have to note that all there is no relative orientation between frame B and frame A, right? ZB and ZA are aligned, XA and XB are aligned, YA and YB are aligned. So if both of these frames are aligned, you can simply take a vector sum of both of these points. But if they are not really oriented, for example, see here XA and XB are aligned, YA and YB are not actually aligned, right? It's a bit different. So then how would you describe the point Q, the position of point Q with respect to position of frame A? How would you describe that? So what do you do is that if the position of point Q is given or it's known with respect to frame B, for example, position of point Q with respect to B is known, and we also can figure out the rotation matrix of B with respect to A, right? If we can also figure out rotation matrix of B with respect to rotation matrix of A, then position vector of P, position vector of Q with respect to A is given by this expression. Right? We have to pre-multiply the position vector with respect to B with respect to the rotation matrix. Right? And we also already know how to determine the rotation matrix of a frame B with respect to another frame A. So here in this instance, we would simply consider frame B and frame A to be coincident, but they are not oriented. Like you can consider the distance between the origin of either of these frames to be 0, but I have only given a gap to, just to make this thing more clear. You can consider this offset to be 0. If this is given, if position of P with respect to Q is given, and we can also find out the rotation matrix between B and A, B with respect to A, then we can actually find out the position vector of Q with respect to A using this following transformation. So combining both of these principles, pure translation and pure rotation, we can describe the position of Q at an arbitrary position as well as at an arbitrary orientation. For example, if the point Q is fixed to the frame B, right? So whenever the frame B rotates, the Q also rotates with frame B, or as frame B moves, Q also rotates with frame B. So the position vector of point Q with respect to A is the position vector of frame B with respect to position vector of A plus this vector. Again, for example, let's just by using that vector addition, position vector of Q with respect to A is position vector of B with respect to A plus position vector of Q with respect to B. Right? Again, this is nothing but a simple vector addition. But if you simply take the vector addition and if the frames are not aligned, you may notice that the superscripts over here are different actually. These two terms are expressed with respect to frame A, but the final term is actually expressed with respect to frame B. So that will give you the wrong results. So before doing that, every single term will have to be converted into a single frame or the frame at which we are interested. So we can do this by pre-multiplying it with the rotation matrix. So rotation matrix between B and A, right? So this term now will become position vector of Q with respect to A. So all the terms will be now with respect to a single frame of reference. Now it becomes homogeneous and you can basically add vectorially. And instead of splitting this position and rotation separately, you can combine, the translation and rotation with a single operator or a single transformation matrix, right? So we'll look more details into it. So this transformation matrix is an operator which maps one frame to another in matrix form. So this homogeneous transformation matrix is a 4x4 matrix that maps a homogeneous position vector from one frame to another. Like, for example, if you have a position vector, described with respect to one frame B, and you want to describe that same position vector of position and orientation of that same point with respect to a different frame A, then you can do so by using the transformation matrix, where the first 3x3 elements is the rotation matrix between A and B, and the final column or the fourth column, the first three elements of the fourth column is basically nothing but the position between the two frames A and B. The first 3x3 items would be the orientation, the rotation matrix between A and B. And for the final row, the first three elements would be 0, 0, 0, and the last element would be 1. So the final column of the homogeneous matrix would always be 0, 0, 0, 1. And if you want to know the transformation from B to A, this is the transformation matrix. You can also do the same thing, the inverse of it from A to B by inverting this matrix, actually. So the inverse of the transformation matrix is nothing but this one as depicted here. So the first 3x3 element would be the rotation matrix transposed or inversed. Either are same because the rotation matrix is either orthogonal. So that makes the inverse as equal to the transpose. And this, the position vector for the inverse matrix would be given as per this expression. And just like before, for any homogeneous matrix, the final row would be 0, 0, 0, 1. That is how it is going to be. Yeah. And the expression that you got here can be easily be obtained. For example, so if A transpose B is so ATB is given as the rotation matrix, which is a 3x3 matrix, and the position matrix, which is a 3x1 vector, and the final row would be 0, 0, 0, 1. And if your objective is to find out ATB inverse, so for the time being, you can consider the rotation matrix to be an unknown 3x3 matrix, the position vector to be an unknown 3x3 vector, and the final row as 0, 0, 0, 1. But you also know that, I'll write over here, the transformation between B and A and its inverse, ATB inverse, is always going to be an identity matrix because matrix multiplied by its own inverse would be an identity matrix of similar form. Right? So if you combine all these things, you will get two expressions. The rotation matrix multiplied by this x would be an identity matrix. I would call this as equation 1. And if you multiply the second columns here, it would be, the second equation would be the rotation matrix multiplied by y plus the position vector between from B to A. This would be, if you compare this and this, it would be 0. This is equation 2. So what is this x? The unknown orientation x would be ARB. If you take this to the other side, x would be ARB inverse or ARB transpose, both are same. And y would be minus APB ARB transpose. So that makes the inverse of the transformation matrix as rotation A B transpose minus ARB transpose APB, and the final row being 0, 0, 0, 1. Right? Or if you have the numerical value, you can simply take the inverse of that 4 by 4 matrix to get the inverse transform. And one final thing to note is that if you have a frame of reference like this, for example, x, y, and z, and another frame of reference, I'll call this as xa, ya, and za, and another frame of reference, xb, yb, and zb. So rotations actually can happen in two ways. Either you can always represent the rotation with respect to the fixed frame of reference. So like if you consider frame A to be fixed to the ground, you can actually you can realize any arbitrary orientation for frame B using successive rotations about axes A, xa, ya, or za, which are the axes of the fixed frame. So either you can modulate or manipulate B using fixed rotations along xa, yk, and za. That is one way. Or you can rotate about the current frame of IB. For example, if you rotate about XA, you will have one configuration of frame B, and subsequent rotations would be about the subsequent frames. For example, if you now got frame B, if you rotate about XB, you will get another frame. You can call it as C. Then if you rotate it about the one axis of frame C, you will get another axis, so and so and so forth. So as you know, since the matrix multiplication is not commutative, depending on which frame of reference you use for rotation, you will have to either pre-multiply or post-multiply the compound rotations. For example, as per this statement, if the mobile frame is to be rotated by an angle theta about the kth unit vector of the fixed frame, then pre-multiply. So if the subsequent rotations are with respect to the fixed frame, you always pre-multiply the subsequent rotations. Or if the mobile frame is rotated by an angle of theta degrees about its own unit vector, then post-multiply the rotation matrix. So for subsequent rotations, you will post-multiply, or you multiply towards the left-hand side for substitute, to the right-hand side towards the subsequent multiplications. Pre-multiply or post-multiply, depending on whether it is with respect to the fixed frame or with respect to the moving frame. Okay, so with that, we will solve a few sample tutorial problems which are relevant to week 1. So yeah, the first question is, in an effector, the effect of locomotion on the environment causes the motion of the effector itself. So out of which of this option is the correct option? Is it locomotion, Is it manipulation, multiplication, accumulation, complex motion, or slew motion? So like we have actually considered two different classes of effector, if you can recall. The first one being manipulators, and the second one being locomotive devices or mobile robots. And the process itself is called locomotion. So if the effector causes the motion of the objects around it, then we have such effectors are called manipulators. And if the effector of the if the effect on the environment causes the motion of the effector itself, then such process is called locomotion. And examples of locomotion devices are mobile robots. So for in this case, for the problem one, I hope you will all agree that the correct option is locomotion, because the question specifically asks the motion of the effector itself. So I hope that is clear. Yeah, checking the answer, the option one is correct. Okay, moving on to question two. So it's a fill in the blanks kind of a question. So this robot, a dash robot manipulator has more than one loop, or in brackets, end effector is connected with multiple serial chains. Like for example, if we have a platform like this on which we mount a tool, and we also have a ground or a fixed base, and as per the question, it says the robot has more than one loops, or it is connected to the ground by multiple serial chains like so. Then clearly this is actually an example of a parallel robot or a parallel manipulator, right? Because in serial, we know that the serial rigid links are connected from head to tail, one to the another serially using joints. And as you can see, there are no closed loops within the serial structure. So that makes this definition an obvious candidate for this parallel manipulator. So if you check the answer, the correct answer is parallel robot or closed chain manipulators. Either option are correct. Okay, so moving on to question three, it says find the rotation matrix C with respect to A. The question asks specifically to find the rotation matrix C with respect to A, and we have the following details for numerical calculations. So the rotation matrix of B with respect to A is given as 0, minus 1, 0, 1, 0, 0, 0, 0, 1. And the rotation matrix of C with respect to B is given as 1, 0, 0, 0, 0, minus 1, 0, 1, 0. And the question is to find out what is rotation of C with respect to A. So from the lectures, we know that from compound rotations, we know that if you multiply the rotation matrix of B with respect to A with rotation matrix of C with respect to B, we will get the rotation matrix of C with respect to A using compound rotations. So we have already been given ARB and BRC are already given. It's only a process of multiplying these two matrices out. So it's 0, minus 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 1, 0. So if you multiply this out, what will be the answer? It will be 0, 0, 1. So it will be 1, 0, 0, 0, 1, 0. This will be rotation matrix of C with respect to A. So I think the correct answer is option A for question 3. Right? So that is indeed the answer. So yeah, question 4 is also another question on rotation matrices. So you have been given a rotation matrix A, R, B as such. You are asked to find out the inverse of the rotation matrix. So if you can recall, the rotation matrix is an orthogonal matrix or an orthonormal matrix, right? You can clearly check, like it's applicable for all the rotation matrix, but if you are in doubt, you can always check that the norm of each of these columns, the length of each of these columns individually is 1. And if you take the dot product of one column with respect to any other column, they are always going to be 0 because they are orthogonal to each other. They are orthogonal, and at the same time, they are also uh, of unit length. So they are orthonormal vectors. So the property of orthonormal vectors is that their inverse is also their transpose. Right? So the question asks you to find inverse. You only need to take the transpose of it. So that makes it 0, minus 1, 0, 1, 0, 0, 0, 0, 1. So which answer is correct? Let's see option A. I think option A is pretty much the correct answer. Yes. Okay, so keep in mind that the orthonormal condition only exists for the rotation matrix, the 3 by 3 rotation matrix, and it's not the case for the 4 by 4 transformation matrix. It's only an attribute of rotation matrix. Yeah, so option A is indeed correct. So moving on to question 5. Now we deal with the transformation matrices. So we have been given a transformation matrix A TB as 1, 0, 0, 5, 0, minus 1, 0, 4, 0, 0, 1, 0, and 0, 0, 0. So if there are two frames, let this be frame A, let this be some other frame B. The position and orientation of frame B with respect to A is defined by this transformation matrix A, TB. We have also been given as one more transformation, which is ATC, that is 0, 1, 0, 10, 1, 0, 0, 5, 0, 0, minus 1, 0, and 0, 0, 0, 1. And let this be another transformation matrix, random. This is C. So transformation of C with respect to A is also given. The question asks you to find the transformation of C with respect to B. C with respect to B is we have to find it out. So again, using the compound transformation, so if you multiply ATB to BTC, you will get ATC, right? If you cancel these terms. And the question is to find out transformation of C with respect to B. This is what we need to find it out. So if you take this matrix to the other side, BTC would be nothing but ATB inverse ATC. If you do this out, you can obtain transformation of C with respect to B. And what is ATB inverse? So either you can, if you have the computational tool, you can take the inverse of ATB and multiply it with ATC, or if you can recall the formula, for example, if ATB inverse is nothing but ARB inverse minus ARB inverse position vector of ARB, then final row would be 0, 0, 0, 1. Right? So what is ARB inverse? ARB inverse is nothing but the transpose of this rotational matrix. So that is nothing but 1, 0, 0, 0, minus 1, 0, and 0, 0, 1. Right? So if that is the case, then what is my ARB inverse APB? This would be minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. You multiply this with the position vector of ATB, that is 5, 4, 0. So what would be your answer? If you multiply this out, this would be 5 minus 4, 0. And if you consider the minus sign, it would be minus 5, 4, and 0. So ATB inverse would be nothing but 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Then this term minus 5, 4, 0. Then the final row would be 0, 0, 0, 1. So this entire thing would be ATB inverse. Then you have to multiply it with ATC over here. So that is nothing but this one. That is 0, 1, 0, 10, 1, 0, 0, 5, 0, 0, minus 1, 0, 0, 0, 0, 1. So if you multiply this out, for example, yeah, I will just move this over here. If you multiply this over here, what will you get? You will get, I think, yeah, you will get 0, then 1. Final entry would be 0. Then it will be 10 minus 5. That will be 5. Second column would be minus 1. Then 0, 0, 0, minus 5, plus 4, that is minus 1. Third entry would be, third row would be 0, 0, minus 1, 0, and the final column would be 0, 0, 0, 1. This would be the final matrix actually over here. Yeah. And the correct answer corresponding to this would be, I think, yes, option A. So this is nothing but ATC. Right? Yes. So now moving on to question 6. What does it say? So question 6 says the rotation matrix corresponding to 30-degree rotation about positive x-axis is, which is the rotation matrix of 30 matrix. For example, if you consider a fixed frame, so if I consider the out of plane axis to be x-axis, and as per the right-hand thumb rule, this would be y-a axis and this would be z-a axis. And if you rotate, if consider a frame B initially coincident with frame A, frame B is also initially coincident with frame A. Now you are rotating 30 degrees with respect to this positive x-axis, x-a axis. Now the y-axis would be, parallel to, sorry, the xb axis would be parallel to xa axis, because originally they were all coincident. You are rotating with respect to x-axis, and xb would be now XP would still be with respect coincident with XA. YB was initially like this, but since we are rotating with respect to XA axis, it will be like this. So this would be YB, and ZB would be like this. This would be ZB. And if you can recall the how we can actually fill out the entries of the rotation matrix, the first entry would be the angle between XB axis and XA, Y, and ZA axis. So XB with the dot product of XB with XA is XB XA cos 0, that is 1. Angle between XB and YA is 90 degrees, so that makes it 0. XB with ZB is 0, right? And now this is 30 degrees. So the second column would be the angle between direction cosines between YB and XA, YA, and ZA axes. So angle between YB and XA would be 90 degrees, so that makes it 0. YB and YA is direction cosine is cos 30. And YA and YB and ZA is this projection, that will be sine 30. And the third column would be the projection of ZB on XA, YA, and ZA axis. ZB on XA would be 0. ZB on YA would be minus sine 30, because this would be 60, this would be 30, this would be 60. And ZB on ZA axis is cos 30. So this is the rotation matrix with respect to X axis. And the correct answer is, I believe, option A. That is indeed the correct answer. Okay, moving on to question 7. So in this image below, you will find Novak Djokovic executing a forehand and a backhand shot. So the first image is actually a forehand shot, right? He is extending his arm as far as he can, and he's only using a single arm. And if you take a look at this backhand shot, this is actually his backhand shot, but to support his backhand, he's using his other arm also, right? So he's holding the racket with both of his arms like this, like a closed chain mechanism. So if your context is given, choose the correct answer from the following options. So the backhand shot is similar to a parallel manipulator architecture. Would you agree with that? If, as you can see, both of these arms are actually attached at this common point where the racket is also attached. So that depicts a closed chain architecture, or a parallel manipulator kind of a structure. So that makes this true. So the forehand shot is similar to a parallel manipulator architecture. That is indeed false. The backhand shot is similar to a serial manipulator architecture. That is also false. Parallel robots inherently have larger workspace than serial robots. No, that is also false. Because the workspace of a parallel robot would be the intersection of the workspace of individual links. So if one individual arm has this workspace, the other arm has this workspace, the combined workspace of the parallel manipulator would be the intersection of the two workspace, which is clearly smaller than the individual workspace. So parallel robots inherently have smaller workspace than serial robots. Parallel robots are inherently superior in heavy duty payload manipulations. That is true, because the loads are equally distributed among multiple arms, so that makes them more suitable to carry more payloads. Serial robots inherently have larger workspace than parallel robots. That is also just with the example that we have considered earlier. So it's a multiple correct answer option. So options 1, 5, and 6 are correct. Yes, first option is correct. And the final two options are also correct. So moving on to question 8. The reachable workspace are those where the manipulators can reach with any arbitrary orientation of the end effector. So reachable workspace are the points where it can reach with any arbitrary orientation. So that is false because, as we have already seen, it's the dexterous workspace that can reach a point with any arbitrary orientation. Reachable workspace is only a set of points where the robot can reach. It does not really mean it has to reach there with all sort of combinations. That is indeed false because this statement is only applicable for dexterous workspace. Yes. That is indeed false. Yeah. Statement is a definition of dexterous workspace, not reachable workspace. Question 9 is also true or false question. If the mobile frame is rotated by an angle theta about the kth unit vector of the fixed frame, then post multiply with the rotation. So if we are talking about fixed frame, if we are continuously rotating about with respect to the fixed frame, then we have to pre-multiply. It's not post-multiply. So again, that is false. Right? If you are continuously rotating about mobile frame of reference, then only it is true. Maybe if you want to see an example, I can show you an example. 1 second. So this is the fixed frame, X, Y, and Z. So now, since this is the only frame, consider if I'm rotating with respect to the fixed x-axis by 90 degrees. So if I'm rotating fixed x-axis by 90 degrees, how will it look like? X-axis will remain the same. Y-axis will go like this. Z-axis will go like this. This is X. Let this be X1, Y1, Z1. Now this will be X2. This will be Y2. This will be Z2. Right? And if I am rotating with respect to fixed Z1 axis, then how will the second rotation will look like? This will be rotation about X1. We'll get this. And now we'll rotate about Z1. So how will this frame will look like if you rotate about Z1? So Y2 will be the same. This will be Y2. And if you are rotating with respect to Z1 axis, positive Z1 axis like this, Y1 would be out of plane, I believe. And sorry, Y2 would be like this. This would come here. So Z2 will be like this. And X2 will move from here. It will rotate from here to here. Right? So if you multiply this out, earlier we had the rotation matrix 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. And now if you rotate it with respect to, the first transformation is rotation with respect to x-axis, pure x-axis. So the x-axis formula would be 1, 0, 0, 0, 0, cos 90 minus sine 90, sine 90, cos 90. So since we are rotating with respect to the fixed frame of reference, I'll just write it here. We have to pre-multiply that with the original identity matrix. So that will be 1, 0, 0, 0, cos 90 would be 0, sine 90 would be minus 1, minus sine 90 would be minus 1, then 0, 1, cos 90 would be 0. Then again, we are rotating with respect to the fixed Z1 axis. Okay. I think this is X2. Yeah. So rotating with respect to Z2 axis, the rotation matrix of Z2 axis is cos 90 minus sin 90, sin 90 cos 90, 0, 0, 0, 0. This is Rx, this is Ry. Sorry, Rz. So cos 90 is 0, minus sin 90 is minus 1. This is 0. Sin 90 is 1. Cos 90 is 0. Then 0. Then 0, 0, 1. So if you multiply this out throughout, finally you will get the rotation. Finally, you will get the rotation orientation of this with respect to the original frame of reference. So like first we'll multiply this out, then multiply this with the pre-multiplication. If we do that, what will we get? If you multiply with these two out, that will be something like 1. Second column, second element would be 0. Third would be 0. Should be 0, 0, minus 1. Then 0, 1, 0. Then you have to pre-multiply that with the third. This would be 0, minus 1, 0, 1, 0, 0, and 0, 0, 1. If you multiply this out, what will you get? This would be, hold on 1 second. This would be 0. This would be 0, and that would be 1. This would be 1, 0, 0. The final column would be 0, 1, and 0. So yes, this is our final answer. So the first column 0, 1, 0 means the y-axis the x-axis is parallel to the new x-axis is parallel to the old y-axis. So this x-axis, new x-axis, x2 is parallel to the old y-axis. And now this column, the second column says the y-axis is parallel to the new y-axis is parallel to the old z-axis. New y-axis, y2 is parallel to old z1 axis. And the third column says the new z-axis is parallel to the old x-axis. New z-axis. This is parallel to the old x-axis. Right? So this was only possible because we pre-multiplied it. But if we do the same thing post-multiply, if we did this post-multiply, then this would have been a wrong answer. We wouldn't have gotten this exact mapping. We would have got some other mapping actually. That would obviously be wrong. And we would only do post-multiplication if you if you rotate about the current axis. So after the first rotation, you rotate about current axis of frame 1, then you rotate about frame 2. That's how it goes. But every time the rotation is about with respect to the fixed frame, you have to pre-multiply. So that was this example. Okay, yeah. Moving on to the final question, question 10. If the operational space variables are given and the geometric variables are known, then finding the configuration space variable is known as, is it transformation, forward kinematics, control translation dynamics, or inverse kinematics? Like we have already covered this during the definition of forward and inverse kinematics. So in the context of a 2R manipulator, we have the two joint variables, theta1 and theta2. Theta1 and theta2 are, we call them as joint variables. Right? You can also call them as configuration variables. And x and y, for example, the position coordinates of the tip or the end effector of this robot, you could call this as task space variables or operational space. The question says the operational space variables are given and the geometrical variables are not. The geometrical parameters are nothing but the length parameters, such as the length of the robot, the length of each of these links, their position coordinates, their width, all these things are the geometrical variables. Then if the operational space variables are given, then finding out the configuration space variables is called, it's the inverse kinematics problem actually, right? If x and y is known, finding out theta2 and theta1 would be the problem of inverse kinematics. And the procedure to do that, we would be covering, we would be covering this, we would be covering solving, inverse kinematics problems of robotic manipulators in week 2. So yeah, checking the answer is indeed week 2. So I think that's the end of the tutorial session for this week, covering week 1 topics. So we'll meet next week with topics regarding week 2. We'll also solve some sample week 2 problems. So until then, thank you. I'm ending this session here. Okay, thank you.